So for this homework, we're going to work with something called the Carnot cycle, and we're gonna first go ahead, derive, and explain the reversible heat and work associated with each step of the Carnot cycle. Then we are going to derive and explain the limiting or the best possible efficiency for a heat engine in terms of the high and low temperatures, heat source, and sink. We're going to explain how this motivates the definition of entropy. And from the second law of thermodynamics, for a constant temperature and pressure, we're going to show that the change in Gibbs free energy is less than or equal to zero. So first, what I'm going to do is I'm going to go ahead, I'm going to move over here. And we're just going to draw out the Carnot cycle. So for the Carnot cycle, we have a pressure axis and we have a temperature axis. Now on the pressure temperature graph here, we have two isothermal curves at two different temperatures. We're going to call this one TH, this is the higher, hotter temperature, and this one is going to be equal, like that. This is going to be a colder temperature, it's going to be a lower temperature. Now, on our curve here, we can define 4 points here. And we are going to call these A, B, C, and D. Now, let's talk about the relation we take for each of these to get to each of these points. So from A to B here, we see that we have this isothermal curve, which will take us from point A to point B. However, to get to point B to point C, we have this adiabatic curve that connects these two. To go from point C to point D, we have another isothermal curve. We're just following on this colder temperature. And to get from this colder temperature to this higher temperature, this point D to point A, back to point A, we have another adiabatic curve. Now this is what we define as the Carnot cycle. And it is this, quite literally, it's a cycle going between these 4 points, which goes along this higher temperature, down adiabatically to a colder temperature, up isothermically to this higher pressure on this colder temperature, and we go back up to that higher temperature curve. So in order to derive for what we want to find out, the first step here is we're going to design a couple systems here. So we're going to start off by designing a system for A. And so our system for A could look something like this, where we have a piston container. And to get from point A to point B, we have another container with the piston at a higher level. So we had already stated beforehand that from point A to point B, it's an isothermal curve. So there's only one temperature, and that is the hotter temperature, the higher temperature. And so we can also then define the heat added as just that heat. We'll just define it like that, just for ease. Now, the fact that we have an isothermal system here, since this is isothermal, we can use that fact to go ahead and derive the equation we can use to find the change in heat from point A to point B. So let's go ahead and do that next. So let's start off with the first law of thermodynamics, shall we? So du, change in the internal energy, is equal to the change in heat minus the change in work. And we can rewrite this equation as such. Cv times dt is equal to dq minus p dv. Now, since we said that this is an isothermal system, what we can end up doing is we're going to set this side equal to 0, and we're going to bring this term over here and set them equal to each other. So in the end, we have dq is equal to, and for this p here, we can use the ideal gas law, PV equals nRT. We're going to assume 1 mole, so P is equal to RT over V. So this is going to be equal to RT over V dV. Now, since these both have these differentials in here, we can go ahead and integrate both sides. For this one, we're going to go for 0 to QH, which is what we are trying to find out up here. And for this one, we're going to go from the volume in A to the volume in B. And when we do that, we get, let's see, we just get QH. Because when we integrate this, it's 1, and then it's going to be, that's 0 to QH, is equal to, this is 1 over V, so, and RT are constants, so we're going to have RT times natural log of VB over VA. And this is the change in heat from location A to location B on the Carnot cycle. Now, to go from point B to point C, what we're going to end up doing is we'll end up let's assume these are the same size. I just want to show that we are actually heightening our piston even more. So this is at an even higher level than point A and point B. So this is point C here. And this is an adiabatic, it's an adiabatic system here. And so our Q is equal to 0 when we go ahead and do adiabatics. And in more specifics, this is an adiabatic reversible expansion. An adiabatic reversible expansion from point B to point C. Now, from an earlier video, we had let it be known the fact that we go PV to the CP over CV is equal to some constant, and we call this constant gamma, we call this constant K, you could call the constant constant. It doesn't really matter too much. And so when we use the laws of ideal gases, what we end up with is Tc over Th to the Cv over R power is going to equal our volume from B over our volume from A. And this is the relationship we're going to use to go from point B to point C in our adiabatic reversible expansion. Now, to go from point C to point D, we're going to do a very similar thing from point A to point B. It is still that isothermal. It's still that isothermal system. So we are going to end up having some QC. There's going to be some heat removed, and it's going to be that change in temperatures. So the system is going to look something like this, where we are now leveling out the piston at some lower level than we had before, since we are taking away this heat. And so from here, we can go ahead and pretty much set it up the same way. So we'll start with the first law of thermodynamics. Come on. So change in internal energy is equal to change in work change in heat minus change in work. Rewrite this as CV dt is equal to dq minus p dv. CV dt is going to equal 0 because isothermal. And so we get dq is equal to, and remember, using that same law of ideal gases, we get RT over V dV. We're going to integrate both sides. We're going to go from 0 to QC on this side. We're going to go from volume at C to volume at D for this one. And so what we end up with is QC is equal to RT times the natural log of VD over V. I really cannot write today. VD over VC. And that's the relationship we'll use from going to point C to point D. Now the last step in the Carnot cycle is to go back to where we started at point A. So this is going to be, whoa, it's an unruly line. This is going to be another adiabatic compression this time. So we're back at point A. We have an adiabatic compression, so Q still equals 0. Adiabatic, reversible compression. And this is going to look very similar to our adiabatic reversible expansion. So we go back to the fact that we have PV is equal to, PV to the CP over CV is equal to that constant. We go ahead and from that, using ideal gas laws, we go ahead and derive. This time we're going to have TH over TC to the CV over R is equal to VD over VC. Come on, VC. So now we have all of the necessary parts that we need to go ahead and derive the equation for the total work that is done throughout the Carnot cycle. So for this final derivation, we're going to go back to the first law of thermodynamics. So let me write this out. Okay. So not that. I'll use this. du is equal to dq minus dw And I'm going to rewrite this without the differentials in them. So u is equal to q minus w. And that's just going to be significant for the sums of the works, basically. So we can go ahead. We're going to set this side equal to 0. And what we end up with is Q is equal to the negative work. And so our sums of heats, so the sum of heat that we're going to have is going to be this QH and this QC. QH plus QC equals the negative work. So this is the equation that we look at when relating the amount of heat in the system to the amount of work that's done on the system. So part 2 is all about deriving the efficiency now. And when we talk about efficiency, we're talking about the fact that we have some work done over the heat added. So we have from C1, we had already gone ahead, we derived that we have the work done on the system is equal to the sum of the heat that was applied and the heat that was taken away during the reversible compressions and expansions of C1. So we can further simplify this as the work done is going to be the sum of the heats added and removed. Heat added is QH. So we have it in terms of heat. However, we want it in terms of the high and low temperature, as we can see right there. So we can go ahead and we can use these 4 equations here to go ahead and try and do that. Now, we might look at, where's my mouse? we might look at this VB over VA, this VB over VA, and notice that there are some parallels that we can draw. And we can use that information to go ahead and try and get everything in terms of one of these ratios. So let's go ahead and, well, first let's look at this. So we have VB over VA in both of these equations here. Mainly, let's look at this one. However, we see that the temperature ratio on this equation and the temperature ratio on this equation are reversed. And in order to try and get them equal, what we can end up doing is set one of these volume ratios equal to the reciprocal of the opposing one. So I'm going to go ahead and do this by setting VB over VA equal to, and that's going to be the reciprocal of this side, which is VC over VD. Because when you take the reciprocal of this side, we get TC over TH. We have TC over TH here. They're both to the same power. They're essentially equal. However, when we try and this doesn't have any meaning to the original, so what we can end up doing is if we take the natural log of each side, VB over VA equals natural log of VC over VD, we can go ahead and if we reverse the ratio on this side, we get the natural log of VB over VA is equal to the negative natural log of VD over VC. And from there, we can plug that into the original equations. So we have, well, how do we want to do this? We can do it this way. So we have the natural log of VB over VA right here. So we could rewrite QH is equal to the negative RT times the natural log of VD over VC, D over VC, and the heat removed is just how he derived it in the first place. And now using these, we can go back to our efficiency equation, and after plugging everything in, we see that we have the R's that are going to cancel out. We have the natural logs that are going to cancel out here. The only thing that really differs is the fact that we have a hot temperature here and a cold temperature here. So when we go back up, the derivation for this is going to be TH plus TC over TH, which you can further simplify as 1 plus TC over TH. And that is the efficiency in terms of the hot and cold heats, or hot and cold temperatures, not heats. Actually, a really quick fix after looking at this. This is plus up here. However, once we get down here, this actually turns into a minus with the way it simplifies out. So this is actually 1 minus TC over TH. That's the correct derivation. So what we just did here is a very basic explanation of something that we call the second law of efficiency. Efficiency. And if we were to write this out, it would be QH over TH plus QC over TC is equal to 0. This is our second law of efficiency. And it kind of makes sense, because if we look at our Carnot cycle, the term cycle comes from the fact that if you start on any point, because this is a cycle, if you start at any point along this line and you go along the cycle, you're going to end up at that same point. You're going to end up at this every single time when you go through, you put in the work, you do the isothermic, the adiabatic expression, isothermic, adiabatic compression, you're going to end up in that same spot every single time. And so the heat that you add and the heat that you take away at the starting point is going to equal 0. So in order to further explain this, we can go ahead, we can plug in the values that we had determined for QH and QC. So these here. Come on. That one there and this one here. And so when we do that, we get, let's see, TH. So on this side, we get negative R times the natural log of VD over VC plus R natural log of VD over VC. And obviously that's going to equal 0. They're just the plus and minus of the same thing. Just checking the ratio. Yep. Right. So we look at this. We see we have a negative component. We have a positive component. And these are always going to be equal to each other at any point on the Carnot cycle, which is why this Carnot cycle, it makes sense in a way. So when we think about it in terms of this, where we have this differential of reversible heat over temperature, that's essentially what this is talking about. And this is going to be equal to 0. And another reason why this Carnot cycle is so important is the fact that scientists looked at this, chemists looked at this, and they determined that the property for this differential reversible heat over temperature, it's going to get its own name. And that name is entropy. This is how we discovered entropy. This is how we defined entropy. And that is all thanks to the Carnot cycle here. So the last part here is going to ask us to use the second law of thermodynamics, and using a constant temperature and pressure, we're going to show that the differential of Gibbs free energy is less than or equal to 0. So let's start here. We just derived this definition for entropy. And if we wanted to solve this in terms of the reversible heat transfer, we're going to multiply both sides by T and get this dq rev is equal to TdS. Now, before we use our second law of thermodynamics, let's hit the basics. Let's go to our first law of thermodynamics. Where's a good spot? Let's work here. So, first law of thermodynamics, du is equal to dq plus, not yet, too impatient. dw. Inversely, we get du is equal to our dq rev plus pdv. And further on, we can use our predefined TdS plus pdv. And we'll keep this like that. Now we're going to go use our enthalpy equation, which is U plus PV. And so if we take the differential of each of these, we're going to get dH is equal to du, and we're going to product rule this. We're going to get PdV plus VdP. Now, we have this, what am I trying to say here? I think I'm trying to say, oh, I made a mistake. This is minus, we have a minus dW. I rewrote that wrong. So let's go ahead. We're going to use this du. We're going to plug it into here. So what we end up with is dH is equal to T ds minus P dV plus P dV plus V dP. And so these terms are going to cancel out, and we end up with dH is equal to T ds plus V dP. And here's another equation we're going to keep. So now we can use our knowledge of Gibbs free energy. So G is equal to enthalpy minus the entropy times T. And so let's go ahead, let's do the same thing, take the differential, dH minus S dt plus T ds. So now what we have here is we have this relationship between dH that includes this TDS. So first things first, let's go ahead, we're going to multiply that negative through S dt minus T ds. And dH is equal to TDS plus VDP. Minus S dt minus T ds. We're going to have these cancel out. And we end off with dG is equal to VDP minus S dt. So now we can go ahead and we're going to use the second law of thermodynamics to go ahead and finish off this derivation. So the second law of thermodynamics didn't like that line. Second law of thermodynamics states that differential of entropy plus a differential of entropy of the surroundings is going to always be greater than or equal to 0. And so we can go ahead and we can use our definition of entropy, so ds plus dq rev over t is greater than or equal to 0. And we can go ahead, we're going to multiply each side by t plus dq rev greater than or equal to 0. And let's use our first law of thermodynamics here as well. Make sure it's not missing out on all the fun. dq minus dw, aka dq rev is equal to du plus p dv. We're going to plug that in here. TDS plus du. Oh wait, sorry, there should be a minus here. Come on. Minus du minus pdv greater than or equal to 0. Now, it was stated earlier that we are keeping our pressure and temperature constant. So P and T constant. So what we can end up doing here, since those are constants, we can put them inside of the differential. So this is going to be the differential of Ts minus the differential of U minus the differential of PV greater than or equal to 0. And what we're going to do, we're going to go ahead and negate each side. And by negate, that's just multiply -1. And we're going to switch the sign here. So let's put all this under one differential. So d of, let's go u plus pv minus ts is less than or equal to 0 because we multiplied each side by -1. And we see that we have our definition of enthalpy right here. So we can rewrite this as dH minus Ts less than or equal to 0. And here we have our definition of Gibbs free energy. So now what we have is dG is less than or equal to 0. And we have proven that with a constant temperature and a constant pressure, that the differential of our Gibbs free energy is less than or equal to 0.